Mathematics is full of problems that seem simple at the first glance, but some of them have resisted the greatest mind in history for centuries. This is the story of one of those problems. I'm Saba, and this is Hidden Math.
China, Xiamen. Year 1954. Air raid sirens echo across the city. People rush toward shelters. The People's Republic of China is bombing nearby islands to take control away from opposing forces. But the troops stationed on those islands don't stay idle. Very quickly, both sides come under heavy artillery fire. Inside one of these shelters, a 21-year-old young man named Chen Jingrun is sitting. While everyone else is restless and waiting for the explosions to end, he is reading a mathematics book. Because he has a more important mission for himself: to solve one of the oldest problems in mathematics. The problem is so simple that even a child can understand it. But even the greatest mathematical geniuses in history have not been able to solve it. It's so important that in the year 2000, a prize of $1 million was offered to anyone who could solve it. Yet for nearly 300 years, everyone who tried has failed. So what is this problem? The problem asks, can every even number greater than 2 be written as the sum of two prime numbers? Anyone familiar with even numbers and prime numbers can understand this easily. But let's go through a few examples. For example, the number 6 is an even integer. Can we write it as the sum of two prime numbers? Prime numbers are numbers divisible only by themselves and 1. So 6 equals 3 plus 3. We can test this for more numbers. 10 equals 5 plus 5, or 3 plus 7. 42 equals 37 plus 5. There's also a more systematic way to visualize this. We draw two diagonal lines. Along each line, we write prime numbers in order: 2, 3, 5, 7, 11, and so on infinitely. On the other side, again, 2, 3, 5, 7, 11, and so on. Now from each prime number, we draw a line parallel to the opposite side of the triangle. Wherever these lines intersect, what do we get? We get the sum of two prime numbers. For example, 2 plus 2 equals 4. 3 plus 3 equals 6. 5 plus 3 equals 8. As we continue, we get more and more sums. The key point is this. As we go further down, not only do all intersection points become even numbers, but their number increases. But the main question is, does this always happen? That's what we call a conjecture. Something not proven yet. And this one is called Goldbach's Conjecture. Let's go back to China and to Chen. Chen's obsession with this conjecture goes back to his high school years. One day, his teacher stood in front of the class and said, "Mathematics is the queen of the sciences. Number theory is the crown of that queen. And Goldbach's conjecture is the pearl on that crown." Then jokingly, the teacher added, "Maybe one of you will solve it someday." The whole class laughed, except Chen Jingrun. Later, Chen said, "I didn't laugh because I didn't dare. I was afraid my classmates would discover my dream." But he never forgot that lesson, to always remember the pearl on the crown and never forget his dreams. Now, we talked a bit about Chen, but we haven't said much about Goldbach himself, the person this conjecture is named after. To be honest, there isn't that much to say about him. Christian Goldbach was a fairly ordinary and relatively unknown mathematician from Prussia. Prussia is no longer an independent country today and has its own history. But if you've seen the story of the Königsberg bridges, you might be somewhat familiar with that city. Goldbach was born in Königsberg in the early 18th century. At first, he studied medicine and law and only occasionally worked on mathematics. At the age of 20, he decided to begin a long journey that lasted 14 years. A journey of more than 400 kilometers, which for that time was a lot. The purpose of his journey was to meet some of the great mathematicians of his time, such as Gottfried Wilhelm Leibniz, one of the two inventors of calculus. In London, he met Isaac Newton and members of the Bernoulli family, some of the greatest mathematicians of all time. Eventually, he ended his European journey in Russia, where he stayed and joined the newly established Academy of Sciences in St. Petersburg. It was there, in the year 1727, that he met the most important person in his scientific life, a 20-year-old mathematical genius named Leonhard Euler. They had something in common. What they shared was a mutual obsession with number theory, so they became friends very quickly. In the year 1729, Goldbach moved to Moscow. But for as long as Goldbach lived, for 35 years, the two continued exchanging letters. In one of those letters, Goldbach wrote a sentence in the margin. It wasn't exactly the same form of the conjecture we know today, but it was something related. He suggested that every integer greater than 2 could be written as the sum of 3 prime numbers. Euler liked this statement, but he thought it could be expressed more clearly and more precisely. To him, it seemed logical that odd numbers might require 3 prime numbers to be constructed. But then he turned his attention to even numbers and thought, well, if odd numbers can be built using 3 prime numbers, then maybe even numbers only need the sum of 2 prime numbers. After that, Euler wrote a letter to Goldbach, explained that Goldbach had actually mentioned this idea before during one of their face-to-face conversations. So Euler rewrote the idea into 2 separate conjectures. First, every odd number greater than 5 can be written as the sum of 3 prime numbers. This is known as the weak Goldbach conjecture. Second, every even number greater than 2 can be written as the sum of 2 prime numbers. This is known as the strong Goldbach conjecture. The terms weak and strong come from the fact that if you prove the strong version, then the weak version automatically follows. Because you can always take a sum of 2 prime numbers and add another prime, like 3, to get an odd number. So proving the strong conjecture means you've also proven the weak one. But the reverse is not true. After Euler reformulated these conjectures, he was so confident in them that he wrote, "I consider this to be a completely certain theorem, although I am unable to prove it." He never proved it. And for 15 years after that, no progress was made. Then, in the year 1900, David Hilbert gave a lecture at an international mathematics congress. In that lecture, he listed 23 of the most important problems of the 20th century. Problem number 8 was entirely about prime numbers, including Goldbach's conjecture. What Hilbert did was bring this nearly forgotten problem back into the spotlight. But this time, mathematicians began looking at it differently. Let's go back to our pyramid of prime numbers. This structure is symmetric. If 2 primes on the right add up to an even number, the same number appears on the left. So instead of counting everything twice, we can just look at one side. What we observe is this. For small even numbers like 4, 6, and 8, there is only one way to express them as the sum of 2 primes. But as numbers grow larger, like 20, more combinations appear. And the larger the number, the more ways there are to express it. So mathematicians started asking a new question, not just whether every even number can be written as the sum of two primes, but in how many different ways it can be done. Let's express this mathematically. We define a function called h of n. Here, n is an even number, and h of n represents the number of ways to write it as the sum of two prime numbers. For example, h of 4 equals 1, because there is only one way. 2 plus 2, h of 20 equals 2. Since it can be written as 17 plus 3 or 13 plus 7, h of 42 equals 4. We can calculate these manually, but only up to a point. In 1923, two mathematicians, G.H. Hardy and John Littlewood, tried to estimate this function. To do that, they used one of the most important results in number theory, the prime number theorem. This theorem says, if you take a large number n, the probability that a random number near n is prime is approximately equal to 1 divided by the natural logarithm of n. In words, 1 over the natural logarithm of n. Their idea was this. Suppose we take a large even number, which we call 2 times n. Then the midpoint is n. Now we consider two numbers, a and b, such that their sum equals 2 times n. That means one of them is below n by some amount, and the other is above n by the same amount. Let's call that distance c. So we can say a equals n minus c, and b equals n plus c. According to the prime number theorem, the probability that a is prime is approximately 1 divided by the natural logarithm of n minus c. And the probability that b is prime is approximately 1 divided by the natural logarithm of n plus c. But here's the key point. Since n is very large, the function 1 over the natural logarithm of n changes very slowly. So the value of c doesn't significantly affect it. That means we can approximate both probabilities as 1 divided by the natural logarithm of t, n. Now, what is the probability that both a and b are prime? It's simple. We multiply the two probabilities. So we get 1 divided by the natural logarithm of n times 1 divided by the natural logarithm of n, which is 1 divided by the square of the natural logarithm of n dial. Now, there are about n possible pairs of numbers that add up to 2 times n. So if we add all these probabilities together, we get an estimate for the total number of prime pairs, which is approximately d divided by the square of the natural logarithm of an. If we graph this, we see that as numbers grow larger, the number of ways to express them as the sum of two primes also increases. However, Hardy and Littlewood refined this estimate further. But did they prove it? No. This was only an approximation, not a proof. As they themselves stated in their conclusion, what truly matters is proof. And this was essentially the furthest they got regarding the strong Goldbach conjecture. But when it came to the weak conjecture, they had more success. This story goes back about 10 years before Hardy and Littlewood's work, when Hardy received a letter from a completely unknown mathematician from India. Yes, Srinivasa Ramanujan, who is no longer unknown today. Ramanujan began his letter like this. I am now about 23 years old. I have had no university education, but I have completed school-level studies. And since leaving school, I have been working on mathematics in my spare time. Then he attached 10 pages full of results, over 100 theorems, some of them extremely advanced. Theorems without proofs. Hardy was shocked. He had never seen anything like it before. Some of Ramanujan's results were already known, but many were completely new and seemed almost impossible. For example, the claim that the sum of all positive integers up to infinity equals -1 divided by 12. Hardy wondered, how did he arrive at this result? So he showed the letter to his colleague and friend, Littlewood. They stayed up until midnight examining the notes, and they said to each other, either the author is a genius or he is a fraud. But Hardy especially believed that this could not be the work of a fraud, because the results were too strange and too remarkable to come from an ordinary mind. Only a genius could have produced them. Eventually, Hardy replied to Ramanujan and, as a strict and rigorous mathematician, asked him for proofs. But Ramanujan was not like Hardy. He worked intuitively. He often said his ideas came to him in dreams. He saw results, not the step-by-step reasoning. He had never learned how to write formal proofs, so Hardy invited him to come to Cambridge to explain his results in more detail. But there was a problem. Ramanujan was a deeply religious Hindu, and according to his beliefs, he was not allowed to cross the sea. This belief is known as Kalapani. One night, his mother had a dream. In the dream, a goddess told her, let Ramanujan follow his path. And so, he finally traveled to England and Cambridge. After arriving in England, Ramanujan faced many difficulties, but together he and Hardy achieved an important breakthrough. Around the year 1917, they developed something called the circle method. They used this method to solve various problems in number theory. Later, Hardy and Littlewood expanded this idea further, and about 100 years later, this method became the main approach to studying the weak Goldbach conjecture. Let's review what the weak conjecture says. Every odd number greater than 5 can be written as the sum of 3 prime numbers. But again, we don't just want to know whether it's possible. We also want to know, in how many different ways can it be done? So Hardy and Littlewood imagined a kind of counting machine. The input of this machine is all possible combinations of 3 prime numbers smaller than n. The machine adds each combination together and checks whether the sum equals n. If it does, the machine increases a counter by 1. If not, it moves on to the next combination. In other words, this machine simply counts how many ways 3 prime numbers can add up to n. For example, suppose n equals 11. We start checking combinations. 2 plus 2 plus 2 equals 6, not 11. So the counter stays at 0. 2 plus 2 plus 3 equals 7. Still not 11. We continue until we reach 2 plus 2 plus 7 equals 11. Now the counter increases by 1. We keep going. Eventually, we find another combination. 3 plus 3 plus 5 equals 11. So the counter becomes 2. That means there are 2 ways to write 11 as the sum of 3 prime numbers. But how can we build this machine using mathematics? This journey begins with a function called e to the power of I times theta. This function moves around the unit circle in the complex plane. The angle theta determines how far we rotate around the circle. Now imagine replacing theta with 2 times p times m. Since 2 times pi corresponds to 1 complete revolution, it doesn't matter whether m is 0, 1, 2, or any other integer. We always end up at the same point. Voices speeders. Now Hardy and Littlewood introduced a new variable called alpha and multiplied the angle by it. Alpha is a number between 0 and 1. You can think of it as a slider. If m equals 1 and alpha increases from 0 to 1, the vector makes one complete revolution around the circle. If m equals 2, it rotates twice as fast and completes 2 full revolutions. And for larger values of m, the same pattern continues. Now imagine taking all possible values of alpha and averaging all of those vectors. Mathematically, we write this as the integral from 0 to 1 of to the power of I times 2 pi times m times alpha with respect to alpha. What happens? Every vector is cancelled by another vector pointing in the opposite direction. So when we average all of them, the result is 0. This happens for every value of m except 1. When m equals 0. In that case, we have to the power of 0, which equals 1. So regardless of the value of alpha, the vector always points in the same direction. Its average is therefore 1. This is remarkably similar to the counting machine we wanted. If m equals 0, the output is 1. If m is not equal to 0, the output is 0. Now we replace m with something meaningful. We are trying to prove the weak Goldbach conjecture. In other words, we want to be equal to P1 plus P2 plus P3, where P1, P2, and P3 are prime numbers. We can rewrite this as 1 plus P2 plus P3 minus n equals 0. Now we use this expression in place of m. So whenever P1 plus P2 plus P3 equals n, the expression becomes 0. That means m equals 0, and the integral contributes 1. Whenever the sum is not equal to n, the expression is non-zero, and the integral contributes 0. At the moment, however, this construction checks only a single combination of 3 prime numbers. To count all possible combinations, we need to add a summation over all prime numbers. This gives us a function called h of n, which counts the number of ways that n can be written as the sum of 3 prime numbers. Let's test it for n equals 11. If we compute it, we get 6. But earlier we said there are only 2 ways. Why 6? Because the machine counts different orders separately. For example, 2, 2, 7 has multiple arrangements. 3, 3, 5 also has multiple arrangements. So although there are 2 unique combinations, the formula counts 6 permutations. We can adjust for this later. But for our purpose, this machine works well. Now we have a of n. We just need to show that for every odd number greater than 5, this value is at least 1. That would prove the weak Goldbach conjecture. But if you've been paying attention, there are 2 problems with this approach. The first problem is that we are assuming we know all the prime numbers smaller than n. That works fine when n is small, but when n starts growing toward infinity, we obviously don't know all the prime numbers anymore. The second problem is that as the number of prime numbers increases, the number of possible combinations grows explosively. For example, if n is 1001, there are 1,229 prime numbers smaller than it. That means there are more than 310 million possible triples of prime numbers to check. And if n is increased to 1 billion, the number of possible combinations rises to nearly 22 sextillion. That's about 1 billion trillion. Or written another way, about 10 to the power of 21, a 1 followed by 21 zeros. So the bottom line is that this approach doesn't work as easily as it might seem. The number of possibilities grows so quickly that even the fastest computers would struggle to check them all one by one. So Hardy and Littlewood came up with a much smarter approach. By moving the summation inside the integral, they completely change the nature of the problem. Instead of using brute force computation and checking every possible combination of prime numbers one by one, they began analyzing the collective behavior of all prime numbers simultaneously. To see how this works, let's expand the exponential term. We can rewrite it as a product of 4 exponential functions. The first 3 exponential factors are actually identical in form. The reason is simple. There is nothing that distinguishes P1, P2, and P3 from one another. They are all prime numbers chosen from the same set. So rather than writing these sums over and over again, we can bundle the entire collection into a single function. Let's call that function S of alpha, an. With this notation, the expression becomes much more compact. In the end, h of n depends on 2 pieces. The first i's to the power of negative I times 2 pi times n times alpha, which is simply a known factor that we can compute directly. The second is our new function, s of alpha, n raised to the 3rd power. So instead of dealing with countless individual prime number combinations, we only need to understand the behavior of this single function, s of alpha, n. Now let's return to our example where n equals 11. In this case, s of alpha, 11 is equal to the sum of 4 exponential functions, one for each prime number less than 11, 2, 3, 5, and 7. To visualize this, imagine each exponential term as a rotating clock hand. Each clock has its own speed, and that speed is determined by its prime number. For example, 2 rotates the slowest, then 3, then 5, and 7 rotates the fastest. But remember, this is a set. So we need to add all these clocks together. To do that, we place them head to tail like vectors. The final vector we get is the result of adding all of them. Now watch what happens as we increase alpha. Each clock rotates at its own speed. What matters to us is not the behavior of one clock, but the combined behavior of all of them. If n is small, nothing too unusual happens. But if we take a larger number, say 99, then we have about 25 clocks. Now as alpha changes, all clocks rotate at different speeds. At first, everything looks chaotic, like a swirling pattern. But then something interesting happens. When alpha reaches 1 divided by 6, suddenly many of the clocks align in similar directions, and we get a large resulting vector. Then, as we increase alpha further, they cancel each other out again, until we reach another special point, 1 divided by 3. Again, many vectors align and we get another large result. This strange pattern repeats. For most values of alpha, the vectors cancel each other out. But at certain special values, they align and reinforce each other. Why does this happen? Let's look at the case where alpha equals 1 divided by 2. That means each prime number is effectively multiplied by 1/2. In other words, we divide each prime number by 2. Now let's make a table. First column, the prime number itself. Second column, the result of dividing it by 2. Third column, the remainder after division by 2. For example, 2 divided by 2 gives 1, remainder 0. 3 divided by 2 gives 1, remainder 1. 5 divided by 2 gives 2, remainder 1. Now, the number of full rotations doesn't matter. What matters is where the hand of the clock ends up, and that depends only on the remainder. We notice that all primes except 2 have remainder 1 when divided by 2. So all those clocks end up pointing in the same direction. That's why we get alignment. Now let's divide primes by 3. The remainders can be 0, 1, or 2. Only the number 3 has remainder 0, so its clock points to the right. The others follow a pattern. Some correspond to 1/3 of a full rotation, which is 2 times pi divided by 3. Others correspond to 2/3 of a rotation, which is 4 times pi divided by 3. In both cases, many vectors point in similar directions. This is called constructive interference. Constructive interference means when vectors align, they add up and reinforce each other. But when alpha is an irrational number, the remainders are not regular or repeating, so the vectors spread out in all directions. When we add them, they mostly cancel each other out. This is called destructive interference. Hardy and Littlewood realized they could use this behavior. Imagine plotting the magnitude of the resulting vector around the circle. They observed that most of the contribution comes from a few small regions. They called these regions major arcs. The rest of the circle, where contributions are small, they called minor arcs. This allowed them to split the problem into 2 parts. The major arcs, which give the main term of the formula, the actual count of ways, and the minor arcs, which represent small errors. They showed that if the generalized Riemann hypothesis is true, then the main term grows faster than the error term. So beyond a sufficiently large number, call it k, the value will always be greater than 1, which means the weak Goldbach conjecture would be true. But there were still problems. First, they assumed the generalized Riemann hypothesis is true, but it is not proven. Second, they didn't specify what that number k actually is, so we don't know how large a number must be for the result to hold. In 1937, Ivan Vinogradov entered the scene. He proved the result without assuming the generalized Riemann hypothesis. So the first problem was solved, but he still didn't determine the exact value of k. He only showed that beyond some very large number, the weak Goldbach conjecture holds. "19 years later, one of his students finally solved the second problem. He determined that number. Can you guess how large it was? 10 to the power of 5? 10 to the power of 80? 10 to the power of 3,000? No, it was about 10 to the power of 6.8, around 8 million, still a huge number. After that, mathematicians worked to reduce this number further. In 1989, it was reduced to 10 to the power of 43,000. Then it became 10 to the power of 7,194. And by the year 2012, it reached 10 to the power of 1,346. This is much smaller than before, but still enormous. To give you an idea, the number of protons in the universe is about 10 to the power of 80. Even if you turned the entire universe into a computer, you wouldn't have a chance to check all possibilities. So this boundary had to be pushed much lower. After years of effort, in 2013, a mathematician named Harald Helfgott made a breakthrough. He studied new methods and improved previous estimates. Within weeks, he obtained better results than existing papers. At first, he thought he could solve it quickly, but later he realized the problem was more difficult than expected. He needed to do two things. First, push the computational boundary as high as possible. Second, reduce the value of k as much as possible. Working for 8 years, and with the help of David Platt, he checked all numbers up to 8 times 10 to the power of 30. At the same time, he improved the mathematical estimates. Finally, in 2013, he reduced the critical number to 10 to the power of 27, which is smaller than the range already checked by computers. He published his result in a paper titled The Ternary Goldbach Conjecture is True, a title that sounds like a declaration of victory. So nearly 300 years after Goldbach's letter, the weak Goldbach conjecture was finally proven, which means every odd number greater than 5 can be written as the sum of 3 prime numbers, and as a consequence, every even number greater than 2 can be written as the sum of at most 4 prime numbers. However, in reality, this problem is mostly important within the world of mathematics, because Goldbach's conjecture and its variations don't have a direct application in the real world, at least not yet. Still, because the problem is so simple to understand, and because it is one of the oldest unsolved problems, it has a special kind of beauty. When Helfgott obtained his result, like any professional mathematician, he published it on Arquer, an online platform for scientific papers. He said that after finishing the work, he felt a great sense of relief and lightness. But about the strong version of Goldbach's conjecture, Helfgott said, "I don't think anyone will be able to prove it. At least not in our lifetime." The reason is that the method used for the weak version does not work for the strong version. In the weak case, the main term grows faster than the error term, but in the strong case, this does not happen. So solving it requires a completely new idea, a fundamentally different approach that we still haven't discovered. The person who came closest to solving it's the one we talked about at the beginning, Chen Jingrun. In 1956, Chen became known for his mathematical talent. A year later, he joined the Chinese Academy of Sciences. He spent the next 10 years working on number theory, including Goldbach's conjecture. By 1966, using a different method called sieve methods, he made a major breakthrough. He proved that every sufficiently large even number can be written as the sum of one prime number and another number that is either prime or the product of exactly 2 prime numbers. This type of number is called a semi-prime. This was a brilliant result. André Weil said about it, "Following this proof is like walking along the peaks of the Himalayas. You are so high that you've practically entered the stratosphere, the layer of the atmosphere where airplanes fly." This was the closest anyone had come to solving the problem. Chen was extremely excited about his result. He showed it to a colleague who suggested that he should first announce the result and then refine the proof before publishing. But just as Chen announced his discovery, China entered a period of chaos. In May 1966, Mao Zedong declared that bourgeois elements had infiltrated society and must be removed. This marked the beginning of the Cultural Revolution. With Mao's support, radical students known as the Red Guards attacked institutions and universities. They burned books and subjected intellectuals, teachers, and scientists to public humiliation sessions. These were called struggle sessions. People were beaten, forced to wear ridiculous hats, and made to carry signs listing their accusations. Accusations like enemy of the revolution or supporter of capitalism. Across China, the pursuit of knowledge was replaced by fear and political conflict. By 1968, 131 out of 171 senior members of the Chinese Academy of Sciences in Beijing had been persecuted. Many of them lost their lives. Chen was one of the targets. He was forced into manual labor. He lived in a small room made from an old boiler without electricity. The Red Guards insulted him, spat on him, and beat him so badly that he sometimes lost consciousness. In one report, it is said that this situation became so desperate that he attempted to take his own life by jumping from a building. Fortunately, he survived. Despite all this, Chen secretly continued working on mathematics until September 13, 1971, when a close associate of Mao died in a plane crash. This event weakened the unity of the Communist Party, and gradually the Cultural Revolution began to fade. But Chen now faced a dilemma. On one hand, he wanted to publish his proof. On the other hand, he feared criticism and attack from authorities, so he consulted Hua Gang, the head of the Mathematics Institute. Hua told him, "The result is correct. You must publish it." And so, in April 1973, Chen published his theorem. 3 years later, Mao died, and the Cultural Revolution came to an end. A famous journalist named Xu Qibai came interested in Chen's story. He wrote an article about Chen's achievements and suffering. It was published in the most widely circulated newspaper in China, and millions of people read it. The same government that had silenced Chen 10 years earlier now praised him as a national hero. His story was told in schools, books, and even films. In 1996, an asteroid was named after him. Imagine if Chen had never published his work. No one would have known about his achievements, his dreams, or his struggles. Maybe only a single sentence would remain. "I have a proof, but I will not show it to you." Very often, it is we ourselves who hold ourselves back, when instead, we should try as much as we can and share the results of our work with the world. Then let the world judge it. Although Chen came incredibly close, he never had the chance to reach his ultimate dream: solving the strong Goldbach conjecture. One possible reason why this conjecture is so difficult is that it might not even be true. If it is false, then to prove it false, we only need one counterexample: an even number that cannot be written as the sum of two prime numbers. In 1931, a mathematician named Niels Pipping checked all numbers up to 100,000 by hand. He found no counterexample. Later, modern computers extended this search to about 4 quintillion. That is, 4 times 10 to the power of 18, and the conjecture held for all of them. We can also use computers to check something else. How many different ways each number can be written as the sum of 2 primes? When we plot this data, we get a pattern that looks like a comet. That's why it's called the Goldbach Comet. This graph shows that as numbers grow larger, the number of representations also increases. Just like the pyramid we talked about earlier, the only way this conjecture could fail is if, at some extremely large number, this pattern suddenly breaks, and the number of representations drops dramatically. But has that ever been observed? No. All computations so far, up to 4 quintillion, show smooth behavior with no sudden drop. But this still doesn't prove anything, because even 4 quintillioni is not that large compared to all numbers. So we need a smarter approach, a completely new idea. As far as we know, Goldbach's conjecture doesn't directly affect other branches of mathematics and doesn't seem to have real-world applications. So you might ask, why should we even care about solving it? But looking at it this way misses the point. What if proving it opens the door to entirely new areas of mathematics? We don't have a complete view of mathematics. We only know what fascinates us. So it's better to work on something that truly interests you. Because when you're interested in something, you think about it constantly. In the shower, while driving, everywhere. And maybe that passion leads to a great discovery. We don't always know what is important or what is useful for the world, but we do know what we love.